Okay, good evening, everyone. And here we have week 12. So basically, the last class, but we have one more revision class. So, according to the course will complete in the today's class. And we will see uh, the multiple linear regression analysis and the after part of that in this class. Okay, so good evening, everyone. I'm Kamna Mishra from School of Mathematical and Statistical Sciences, IIT Mandi. This course is basically instructed by Professor Salab, who is from Department of Mathematics and Statistics, IIT Kanpur. And uh, this in this week 12, we will see these topics, and these are some useful links for this class. Okay. So, in the last class, we have seen what is multiple regression analysis, linear regression analysis. Now, we have seen that in simple linear regression analysis and multiple linear regression analysis, the difference is that in the multiple, the independent parameters increases, and we can increase uh, like according to our need of model. Okay, so now in the today's class we will see the analysis of variance. After this, we will see the goodness of fit. So there are a lot of measures how correctly your model is fitting. Okay, now in that, so a very first was that we have seen the t statistics. So in the last class we have seen that we have here the parameter, here the t statistic, and here at the last column there is p value. Okay, so let me just run it one time. Okay, so this was regarding the last class. Now what we have seen is that these were some plots, and here, if I will go through this summary. Now, so first what we have seen is that here this is the t value, and this is the probability it is greater than mod t. So from here we have seen that what are the significance. So since I'm taking this randomly, so it is gonna affect the model again and again. So whenever you run, it may happen that one thing is affecting the other. It may happen that one thing may not be affecting the other. So here our dependent one is number of runs, and our independent parameters are number of balls and some previous score and number of days that cricketer has practiced. So you can see from here that p value is less than zero point zero 0.05 for two parameters, which is number of balls and number of days he has practiced. So that means the previous score does not matter. Whatever data we have taken based on that. So now it can change. Once you change the values, this will also change. So this is the first test. You can see that test of hypothesis. Based on that, we have seen that what are these parameters. Now, uh, there are a lot of questions after that also, that okay, this one is a parameter which is affecting. These are the like number of balls and number of days he has practiced, that matters. But uh, is it like uh, really completing our model? So that means if I want to have number of runs, so just based on that, can I give the information on our number of uh, runs? So that we will see that how other affect, like how other tests says about it, and based on that we will see that okay, whether it is like a good model or not, because just based on that we cannot see that these are the good model. From here we can only understand that these are the significant parameter in understanding the number of runs, but there can be also some other significant parameters which we are leaving here. So that is why we, if we are leaving that important parameters, that then we cannot understand the number of runs just based on these models. Okay, so basically what I want to say is that, let's say you have one, two, three. Let's say you have three parameters, and let's say some four, five. Okay, other parameters. So in between these three, we can see what are affecting and what are not affecting. So basically, in a statistical word, let's say significant or not significant. Okay. So let's say in between these three, you have got this first and say third to be significant. So it is okay. But it may happen that there are other two parameters, 4 and 5, which are also significantly affecting the model. But since we have not considered it, we cannot have any result based on that. So that is also important, that okay, you have two significant parameters, but is it like really enough for your model? Okay, so for that we will see this analysis of variance firstly, uh, that how overall adequacy of the model, and second we will see the goodness of it. In that goodness of it, we will see that how good it has fitted. That means it has fitted, okay, but how good it is fitting. Then at the after that we will see this regression, lasso regression, and at the end we will see multicollinearity and ridge regression. So these two are the later topics. Firstly we will go through these topics. Okay. Is there any question or okay, no. Okay, cool. Okay, so basically, whenever we do these tests, so our null hypothesis is that H naught, which is beta 1, beta 2, up to beta k equal to 0, and our alternate hypothesis is that any of it is not equal to 0. So, any of this, so basically, this is for at least 1 j, which is in between 1 to up to k. So we take that, so null hypothesis is basically that no parameter is significant. So basically when we have all the betas equal to 0, so if the model is y is equal to let's say beta naught, beta 1, x1 plus beta 2, x2 up to beta k xk. So if all the beta i's are 0, that means that it is simply 0, y equal to 0. So we do not have uh, anything uh, any information regarding that model. So that is the null hypothesis, and alternative hypothesis is any of them, at least one of them is not equal to 0. Okay. Okay. So what happens till now? What we are dealing with? We are dealing with the total variation. Okay. So let me show you the last class. Okay. Okay, so whatever variance we have, this is our variance. So this is our total variance. Now, the total variance in that total variance, this is the sum of the regression plus the residual, because the line we have y is equal to x beta plus epsilon. So now we will have the sum of square due to for the whole regression that will come because of the total one with come. Now these betas are regression parameters, so it will come with the regression, and now this one is the residual. Okay, so these total come with this. Okay, so we have this ss total is equal to ss of regression plus ss of residue. Okay. So now what will happen if you have just single parameter for simple linear regression analysis? You will have one this and one ss of regression because you have only one parameter. Now this ss of regression can be further divided when you have the multiple regression. So this can be further divided based on this x1, this x2, and up to xk, like whatever is the number of parameter. So this is ss is sum of squares if there is any confusion.
ना अच्छा है गैस चढ़ गया वो गैस वक्त दो ये खाऊंगा ये
Yogesh, please mute yourself. Okay, so now what we have is that if we want to see this ss of residues, because overall in the model what we try to do, we try to reduce this epsilon I square. If you will see from the simple linear analysis, here. Okay, so when we have started this estimation of parameters, what we have done is that we have firstly defined the model, and we have said that our motive is to minimize this, and the further parameters whatever we have found based on this. So we have found our beta naught and beta 1 based on this, that we want to minimize this. Okay, so here also in that test, what we want to do is that we want to minimize that. So sum of squares of residues. So this is I'm taking the residuals one. Took it because this one is what epsilon. So our multiple linear regression analysis we can write in this way, right? So this y dash y minus b dash x dash y. This is basically ss of total minus sum of squares of regression. So now we want to have the degree of freedoms for all, and then the mean square, etc. So there are proofs for that, all in that uh, class, so you can go through that. So currently I will just write the table so that we can just understand that how in our software, so that means how in real life models it is working. And otherwise if you want to just go through all of it, you can just go through slides. Okay, so now, the test of significance, so analysis of variance, very basic test, ANOVA test. So, ANOVA test we do whenever we try to fit any model, simple linear regression analysis or multiple linear, we try to fit that model. So, we calculate basically that F statistic, and based on that, we say how good it is that. Okay. So now what we have, source of variation. So I'm just writing this directly. Okay. So with what we can have the variance. So the variance can come uh, if we have the total model. The variance can come from the regression part, like if I say our model is this, y is equal to x beta plus epsilon. So the variation, the variability can come from these beta i's, or variability can come because of this epsilon. So basically, our variability can come because of the regression or because of the residuals. And based on that, uh, the regression, uh, okay. And once we find the variability because of this regression and residues, their sum will be the total one, right? Okay, so now the sum of squares, this one will be SS of regression, this one will be SS of residues. Now, the degree of freedom matters. So for the regression, it is k minus 1. For this, it is n minus k. So for this, it is basically we have the k parameters. The degree is k minus 1. And for the residuals, if you may remember in the last class, we have gone through this. When we have done this, uh, hat matrix, and then we have seen this is symmetric, and then we have gone through this residuals, and in the property, I think uh, somewhere we have seen this, this is n minus k minus 1. Okay, okay. So I don't know whether we have written it or not, but from here we have seen that the yes, yes, here I have written. So in the last class, I think I have taken m, beta 1, beta 2 up to m. So right now I'm taking beta k. So here we have seen that this h bar, it has this n minus m, and this h bar is nothing but this residual. From the residual, it can be defined by h bar y. Okay. So right now I'm writing n minus k. So that is same. Okay. And for the total, so total is coming from this and this, so it will be n minus k plus k minus 1, so that will be n minus 1 in total. And then the mean is square, so obviously the mean is square will be in that also, so mean is square will come because of the regression, and here the mean is square will come because of the residuals. And the f is we define as the mean square due to regression divided by mean square due to the residuals. Okay, and that rejection of h naught will be will say that at least one beta I not equal to 0. Okay, so we will do this test in R. Okay, so for this test, all you need to do is write the ANOVA and write the test. Sorry, write the model, fitted model. So if I will do this, so here are the result. So now you can see, okay, this is sum of a square. So let me just take a screenshot of it. Okay. Okay. So now you can see this is the f value for number of bars. This is the f value for number or just say previous score, and this one is for number of days he has practiced, and these are the f values. So you can see that this and this is significant and others are not. So now the sum of squares, so this one is basically x1 x2 x3. So if you compare from here, so these are for the regression. So for the regression part, the regression part is basically this one x1 x2 x3, and for the residual part is this this one is residual part. These are x1 x2 x3. Now, sum of squares, you can see this is the sum of a square due to the x1. This is the sum of a square due to the x2. This is the sum of a square due to the residual. And then you can see that mean square due to the regression. And here you can see this that f value, that how significant is this is. Now the degree of freedom, these are the 1 1 1, and this 16 is basically n minus k minus 1. So n was our 20 minus k minus 1. So this one is our 16. Okay. Now, the total, so here from the R, you can only have the regression and the residuals, you will not have the total one. So, the total you can find based on these values. So, it will be the sum of all of this. So, this one will be the total. For the total, the sum of squares, it will be 292.85 plus 1.64 plus 185.58 plus 501.93, and the degree of freedom is n minus 1, so it is 20 minus 1, it is 19. So this one is our degree of freedom. Now one more thing what you can see from here is that these and these results matches. Okay, so the value is not same because value uh, will will differ when you do the f test, when you do the t test. So test statistic is different, but the result are same. Here also you can see that number of balls and number of days he has practiced are significant. So that means beta 1 and beta 3 are not equal to 0, and beta 2 is equal to 0. And from here also you can see that beta 1 and beta 3 are not equal to 0, and beta 2 is equal to 0. Okay, is it clear? Okay, so this basically we have the individual regression coefficient we have seen. The next test we will see that the goodness of fit. So goodness of fit, you have the answers here only, the multiple r squared and adjusted r squared, but we will try to understand what these numbers basically means. Okay. Okay. So we will have goodness of fit, and for this, what we do is that we try to find this coefficient of determination. coefficient of determination. So what is r square? This r square is called coefficient of determination, and this shows that how well the sample regression line fits to our observed data. Okay. uh, so now the r is square. Firstly, the r square is in between 0 to 1. So if it is 1, that means it is fitting the best. If it is 0, that means it is not fitting at all. And if it is in between somewhere, then we see that how well it is fitting. Okay. So now this is basically given by SS regression divided by SS of total. Okay. So, what does that mean basically? If SS of total is basically SS of regression plus the residuals. So, residuals are basically what we want to do overall. We want to uh, minimize this sum of a square of residuals, because these residuals, these are just epsilon, these are the random one, we cannot do anything in that. So uh, if we have y is equal to mx line, let's say, so this is perfect. Okay, this is the perfect line. But because we are dealing with the data analysis, so we cannot have all the points in one line, so we have this epsilon, that we have some error, but then also we need to minimize it. So when we minimize it, what will happen? The ss total is coming from ss regression plus ss uh, mm, sorry, residuals, right? So when we minimize it, what will happen? This regression part will increase, and when regression part will increase, the this r square value will increase. So this is just, you need to visualize it a little bit, and these all things you do not even need the formula for it. You will just understand it on your own, that when you visualizes that we want to make our model so that the error will be less. So that is how it makes sense, writing this. Okay, now this is similar as you can write 1 minus total. Okay, and this you can write by e dash e and summation of, sorry, yi minus y bar all square. So this is the residual e dash minus e, so e dash or transpose. Okay. uh, so this r square basically shows how good our model. So if it is, I have said already, if it is 0, it is the worst fit. If it is 1, it is the best fit. And if it is 0.95, that means our 95% of variation in y, that can be explained by these explanatory variables. And that means the model is 95% good. 95% good means it is uh, good fitting our uh, y values. Okay. Now what will happen is that we have one more measure, which is adjusted r square. Now why is that? What will happen if you try to add the variables in it, then r square increases on its own. Why? I have said that if I increase uh, number of explanatory variables, this that means these xi's, then r square increases. Can someone say why? Okay, so why is that? So basically, what will happen? You have in the above, you have SS of regression. So when you're adding a new parameter, that epsilon is remaining same or it will decrease a little bit. Okay, because you're adding because of that. But so SS of regression is coming from what? So regression parameters. So if you have x1, you have sum of squares. If you have x2, that will increase. If you have x3, so if you will increase any parameter, then this r square will increase. Now what is the problem? The problem is that r square is increasing, but maybe that parameter is not really good for our model. So like you can see from here, this one is very small, and that is why it is like just when just adding to our uh, basically finding the r square, you can see that okay, it is not making too much effect. But what if it will high? Because right now I have taken the number in between 0 to uh, basically 0.1 to 0.9. So basically I have taken from 0 to 1. That is why the sum of square is less. But what will happen if you will take the number of variables which are not really affecting the model, but also but they are increasing the sum of squares? What I want to say is that you have the variables not significant. Okay, so not significantly affecting our model, but increasing the sum of square of regression overall. So the r square is increasing, but the variables are really not needed. So we do not want that kind of r square. So that is why we have the adjusted r square. So basically, you need to understand in that way that if we are increasing a parameter, or let's say you work in some company and somebody says that just include all these in your model. So what is the first thing you do? You check that whether it is really good or not. I mean, whether it is really significant or not. If it is not, then I'm not going to spend my money or cost based on that. So this is one of the thing which happens with r square, and that this may gives the overly optimistic picture. So that is why we make use of adjusted r square. So there is adjusted r square. Okay, now this adjusted r square can be given by 1 minus ss of residues divided by ss of total, and this is further multiplied by their degree of freedom. So now you can see that if you increase the degree of freedom, so basically if you are increasing this k, this is going to decrease and this is going to increase. So overall, if it is really a good parameter, then it will increase in such a way. So adjusted r square will show that whether it is really good or not. Okay. So now, if this r square or adjusted r square, say because r square is always in between 0 to 1, but if there is some degree of freedom and something like that for which adjusted r square is less than 0, then it will not have any kind of interpretation. Okay. Now uh, the property about this is that if we have uh, if we have the constant term is not in our model, then we cannot define this r square. So this is some, these are some limitations, that if constant term is absent, uh, then r square cannot be defined. Uh, the second limitation, which is very important, is r square is sensitive uh, to extreme values. So it lacks robustness. Now this is one problematic thing, because if your model have that extreme values and we want to fit a model into that, then the found r square may create a problem for that. The third is that we let's say we do some like the basic transformation in our y. So let's say, from the, if we have the real model in terms of y, if we do a transformation, let's say log y, so we can do any kind of transformation for the fitting. So it may be exponential, logarithmic, or trigonometric. So if we do that kind of transformation, then the r square may not be comparable in that term. So let's say I'm saying that I have done some logarithmic transformation to make it easy for modeling or to see the better one, then it may not be able to compare those models. So that is one limitation, that the transformation done on y uh, may lead to comparable r square with real models r square. Okay, so now we will see. Okay, so we have already. Lost my connection. Okay, give it a minute. Uh, okay, yeah. So that transformation may lead to the limitation. Okay, so results we have seen already. This multiple r is squared. So when you see the summary of it, okay. So here, if you see the summary of it, then you can see this line. This is r square, and this is adjusted r square. One more thing is that adjusted r square value is will always be less than r square. So adjusted r square will always be less than r square. Now you can see that the multiple r squared or adjusted r square, that is 0.393. So basically zero point 0.4. So zero point 0.4 is not cannot be considered as a very good fit. That means our model, it is lacking the information it really needs. Okay. Why? Because that one parameter is not really affecting, there are only two parameters affecting it, and then that also the number of balls is more significant, so this one also if not even working on 99%. So the thing is, there may be some other important parameters which we have not included in this model, and that is why it is resulting to the very small r square. Okay. And the when you have, let's say I have included three parameters, and all the parameters are significant, then your r squared and adjusted r squared will almost be equal. Okay, almost, it will never be just equal, but that will almost be equal because all are important. Okay. So this one was regarding the goodness of it. Now my next question is that were you able to install that lasso we needed for this?
Please repeat the last question.
Are you able to that install that lasso which was needed for this class, or later also? We needed this.
Connectivity is slightly poor today. Yes.
So are you able to install and like that package? Huh?
Now it's okay now. Please go ahead.
Okay. So, if now still, if anybody has any problem, so I will just show it one time. So, if there is any problem, so what you can do is that just go CRAN or project this. Minute is a little bit problematic. So, it will show that this is removed from the CRAN repository, and it can be shown on the Achieve, uh, sorry, archive. So from the archive library, you can see that. Uh, okay.
Ma'am, it is not giving.
What?
Cran our project. Then
Hmm.
we'll go to the archives
Hmm.
because we are facing difficulty.
Uh, I have downloaded from here only. Why you are facing any difficulty?
Ma'am, I tried it very hard, but I could not load the library. It is still saying that library is specified. So I tried from other sources, but
Now,
still some of the functions, that covariance and other functions are still not running.
have you downloaded this library I Lasso or not?
Lasso is there, ma'am. This is index of SRC content. We are getting it from CRAN R project, ma'am.
Yes.
CRAN R project, then archives. Let me copy it, ma'am.
Let me write it just in the chat so you can copy. Okay.
CRAN R project.
The net is very slow
R
from my
project.
side. Okay. So this one is,
Archives.
you can go from this. I have written in the chat.
Okay, ma'am.
Because in my case what happens, I did not have r2s installed in my laptop, so that was it was creating the problem in uh, installing
Okay, ma'am.
that
Right,
package.
ma'am. Okay.
So from here you need to just
All right, ma'am.
copy.
We'll do it. Okay.
You can share your screen actually, then we can see.
Okay, let me. No, no, oh, it's okay. I'm getting.
Hmm?
Mozilla.
Okay, so I'm continuing the class. If you will have the problem, then you can see. Okay, so the next one is that
Yes,
is it installed?
yes, yes, ma'am.
Okay, okay. So here is so regression. Okay. So, before moving to what is transfer regression, basically, what we have is that sometimes when, as I have said in the last part, just for the RS square, what will happen? Sometimes we just take so many variables, so it may happen that all are affecting the model. Then it is very good because it may have that these are really necessary. So it may have that sometimes you have 9 to 10 variables, but what will happen? It may create like when you take the inverse of matrix or when you try to predict it, or basically when you try to even run it. So let's say you have, in the real life you will not have just 10 or 20 values, you will have values in lakhs. Okay, so if you have 1 lakh value of one variable and then for the other value variable, so let's say you are adding one variable, that means you are adding that 1 lakh variable, you are giving that to model and then you want to train it. So it may happen that it will create some it will create some time, it will take some time also. If you will do like more, then you may go through the pro versions of it for that software, etc. So you may need to pay for it also. Now what may happen, what we have just seen, that one of it, like out of three, the one was not important. So if it is creating a very minimal change in our model, so that means it is, if it is very contributing very less to our model, then we do not need it basically. Okay, so that means it is irrelevant to our model and then we need to drop it. Okay, so what we want to see is that the multicollinearity, firstly. So multicollinearity. Okay. So what will happen that we assume in, whenever we do these analysis, we assume that our explanatory variables are independent of each other and the correlation between any two variables is ideally zero. So whenever we write this y as beta 1 x1 beta 2 x2, so we even start our model by saying it that our, let us take these x1 x2 xk to be the independent one and y to be the dependent one. So that means they are independent ones, so they are independent among each other also. So we assume from the very starting that these are independent one and these are not correlated, but in the reality, uh, Generally it does not happen. So what will happen if there is a correlation between the variables, then it will increase the variability of the estimates of the regression coefficient, and that may create some problem with the model, and that called the multicollinearity. So what I'm trying to say, uh, let's say, so I work in the climate. So basically, whenever, let's say, I say that if the temperature is high, so it may creates more clouds and it may creates more precipitation. Okay, basic thing. So if I'm saying that temperature is somewhere affecting the precipitation or rainfall, basically somewhere affecting this. Let's say there is a sea level pressure. So if sea level pressure is also affecting this rainfall, now are they two parameters literally completely different? No. So temperature, if the temperature will increase, the sea level may decrease. So that may decrease that sea level pressure, that may change the wind speed, or the, if you see suddenly winds started, then you feel cold at the night time. So that is also changing the temperature. So one thing, we cannot say this, that all are independent in real life. So in real life there may be some possibility of this, but what will happen if these two are dependent, then these two will create some uh, collinearity, some variance will increase. Why? Because uh, here you have just seen this SS of regression, the sum of squares, that is coming particularly from one variable, right? So let's say you take the variance uh, between a plus b. So what will happen? That is variance of a square plus variance of b square plus covariance to covariance of ab. So if there is co-linearity, covariance between these two, then it will increase the variability of the regression coefficient. That is the simple thing. And this term is known as the multicollinearity. And when we increase the number of explanatory variables, so when we increase these x1, x2, xk, so let's say there are three independent variable, but when we add one more, so maybe it is somewhere affecting x1, x2, x3, or maybe some x1 is related to that x4. So when we increase these number of variables, then the chances of occurrence of multicollinearity also increases. Okay. Uh, Now the rich regression, this is used to estimate the parameters under the problem of collinearity. What it does nothing but just create a penalty on that regression coefficient. So what will happen? Let's say you have three parameters. Up to that model is fine. You are adding one more parameter. It is taking some more time. It may be depending on others. So it creates some kind of penalty. Okay. So penalty basically means like you did, like we did here. So we have that r square. So we have done this penalty, that if you increase the number of variables, then it will decrease by this, or if it is not affecting. So that is somewhere called the penalty in that terms. Okay. So that will help from choosing the regression coefficient which are really significant for our model. Okay. And it will also find the irrelevant variables for our model. Okay. So now this uh, is named as that. So which is least absolute shrinkage and selection operator. Okay, so this lasso regression to choose those explanatory variable whose regression coefficient are not zero. Like not zero means not just exactly, but really, really different from zero and really contributing to our model. So this is basically the computer based techniques, and now there are a lot of groups in that, so which are elastic net, group lasso, overlap, etc., etc. So when you work on that model, so in that time you can go through this, that what are the things you need in your work. Okay. Okay, so basically rich regression places a constraint uh, on the sum of a square of coefficient weights, and that can be formulated. So basically we have beta cap rich, and this is argument of minimum. Beta belongs to that r k, and then summation of yi minus xi beta square, I equal to 1 to up to n. Okay, and this is subject to, okay. So now I don't know whether you have heard of this linear programming problem or not, but the linear programming problem is also same. What we have is that we have one function, so this like a function, and it is subject to a condition. So, what you have is that you have a function and subject to a condition means find a value of this function, but uh, always that value always needs to satisfy that particular condition. So in the linear programming problem, we do the same, that we make a problem and we always take the real life constraint, because in the real life you will have some constraint regarding to whatever your problem is. So here we do this as a penalty, and this says as L2 penalty. So L2 penalty, because you have that the penalty you have L2. So L2 norm, there is a L2 norm. So that norm is defined as summation of whatever your x is square. Just a minute. Okay, so this one basically there. I don't know if you have heard of these in the pure mathematics, but there are different kind of norms. L2 norm, and then there is I don't remember, but then there is a norm with that what absolute function. So this one is L2 norm, so that is why we say it as L2 penalty. And then which means our that coefficients that are not free, and that has to satisfy this particular condition. Now it can be, it is not needed like that you have to give this norm only. Okay, so it is not needed that you need to have that similar constant in your model. You can change the constant in your model. Basically we are trying to add some penalty, so you can add that penalty in your model according to that. Now it is no rule like you need to add the sum, like this square one, the absolute one, or something like that. That will happen like with the practice, I think. So the more you do that, you will understand that what works for the model. Okay. So okay, so this is yeah, so what I was saying, in the linear programming problem we use this Lagrange technique for the constant optimization, and here also we are going to use the same. So we have this beta cap rich, and we have this same thing here. So the argument minimum with beta belongs to that rk, uh, summation of yi minus xi cap beta square, and then lambda summation beta j square. So what we are trying to do is that we have just done all these things in here also only. So what I have done is that if you this is the one way that you can do this minimization, and then you can do subject to this condition, or you can just write in this, because ultimately what we are doing is that we are taking this beta j square less than uh, some t star. Just a minute. So here the beta j square, what we are taking, basically we are taking it less than or equal to. So what we can do is that we can just add on this lambda summation beta j square, and we can minimize the whole. So if we minimize this whole, then we do not need to take this constant separately. Okay. Okay, so now the model we used to write till now, that was the SS what we have written till now. So that was uh, I will just write. So y minus x beta transpose y minus x beta. So this was our SS, sum of square till now. Now this is the rich one. So this one will come along with lambda beta transpose and beta. Okay. So this one is our ridge regression. So this one is a ridge sum of square, and the parameters are the beta and that lambda. Okay. Now what we need to do is that we need to have that again whenever we do. So what we do here, we try to minimize that sum of squares. Okay, so to minimize that sum of square, what we do is that we take its first derivative, we make it equal to 0, we take its second derivative, we say that second derivative is greater than equal to 0, and that is why it is minimizing at this point, and that is why we are going to take this lambda and beta i's. So we will do the same calculation here also. So this is the similar one. Whatever we have done for the simple linear regression analysis, multiple linear regression analysis, the same will be happen for the rich regression also, because the only part changing is uh, this uh, RSS. Okay, so the only part changing is lambda beta dash beta. So the first thing what we need to do is that we need to do its first derivative. So its first derivative beta lambda, and then we need to put it equal to 0. So if I do that, so I'm just writing beta minus 2 x bar y plus 2 lambda beta, and just we need to make it equal to 0, and this one will give us beta dash reach equal to x bar x uh, plus lambda I inverse of it x dash y. So basically 2 will be removed, x transpose y will be here, and this part will be in division. So rather than division, since these are the matrix, I have written the inverse of it. So beta dash ridge will be x transpose x plus lambda I. From here it will be lambda I inverse multiply by this x transpose y. Okay. Okay. Now, when uh okay, the thing is that when you have uh x1, x2 up to xk, let's say these are somewhere correlated, then this x transpose x becomes singular. Okay. So the matrix is basically non-singular when you have the coefficients of it. These are not correlated. So if one is correlated, you can write other in terms of that, and that will make your matrix a non in singular. Okay, so you can say that we cannot find in that way we cannot find this, we cannot find this inverse because the singular matrix will not have inverse, right? So that singular matrix will not have inverse, so we cannot attain that. So basically when we add the lambda in that diagonal elements of it, then it makes, so when we add this lambda, so basically this is lambda I, so we are adding the lambda in the diagonals of x transpose x, and that makes is it non-singular, and because of that non-singularity we can find its inverse, and then we can do the ridge regression estimator. So that is one of the need of ridge regression, that if you have the collinearity, if you have the correlation in between, the direct one you cannot find, there is a singularity, and that is why we need the ridge regression. Okay. Okay, so now lasso regression modeling. This one is basically helpful in selecting the a subset from that explanatory variable. So if you have, let's say, 10, there can be a subset of 3, 4, or 5, let's say, variable, and these are the important variables for our model. So this lasso will do basically this subset selection. Okay. Now the lasso minimization problem is can be defined as like you, as I have just said that before, we have defined the ridge regression problem as L2 with L2 penalty, and the lasso regression we are defining with respect to the absolute value. So beta this of lasso can be written as argument, and we want to minimize that beta from this rk summation of this yi minus xi dash beta, sorry, the square of it, and subject to the condition summation beta j less than or equal to t star. Okay, j equal to 1 to up to k, and t star is some value greater than or equal to 0. So here we have this absolute value constant for this. So before we have seen that L2 one, and here we have the absolute constant one. Uh, Now, the process that how we want to choose that lambda, that will depend on these parameters. Okay, here. So the lambda we want to choose, that will depend on that beta 1, and the choice of t, because the constraint we are giving to it. So if our constraint choice like this one is not good, then it will be tough to find that subset which is really good for our model. Okay, so if we take basically the greater t star, then uh, what will happen if we have the greater t star, then we will, there is more likely that we choose those beta star, sorry, those beta j which are significant, so which are away from the 0. If we will take this from the, like let's say this one is, let's say 0. 0.5, then our beta j needs to be less than 0. 0.5, so that is anyway not affecting our model. So we need to take the higher values of beta j so that it can cover all the beta j's which can be good for this. Okay, and now what will happen uh, depending on this lambda. So if we take a very small value of lambda, then it may overfit the model, and if we take a very large value of beta, then it may underfit the model. uh, why? So if because that lambda is basically what, depending on that beta dash and beta. If we take very small values, so this model is basically, this is not contributing anything, this is basically not contributing anything. So the constraint we are giving, constant basically, let's say a condition that you have to satisfy that condition. If that, I'm saying that it is very small, so I'm not really giving it any condition to satisfy, I'm just saying that do it whatever you're doing. So that may create the overfitting. Whereas if I will make the constant very tough, very difficult, that you have to satisfy this higher condition, then it may happen that this underfit the model and it will give the very less parameters. Okay, so these things you can go through again maybe, because just in one go it may not be very easy to understand all of it. Okay. Now what you can do is that between the ridge regression and between the lasso regression, you can do some cross validation. You can find the most suitable for your, and you can, what you can do is that you can predict some values, and let's say you have a data, and 80% of the data you are doing for the training and 20% you are doing for the testing. So do for do it for the regression, rich regression, for the lasso regression. Check which one is better. Check the for the different values, because you have already these values. So predict by your model and see that which kind of lambda, like, basically gradually increase your value of lambda and see that at what point that one is giving the best result for your model. So which one is predicting the best one? Okay. So basically, to perform that cross validation, as I have said, we need to divide the data into two sets. So basically, you can divide two sets. Now that is not necessary to use the 80-20 rule. You can use 70 or 30, 75 or 35, sorry, 75 or 25, whatever percentage suits you. But a large percentage is generally is for the training set, and the smaller one is used for the test set. And what we do is that in the train set, we just train the model, and in the testing one, we, based on that training set, we give more values and we try to predict the uh, like, we have already these values and we try to predict these values, and we see what is the difference between these. And if the difference is less, then our model is predicting very well. Okay. So what you can do is that you can just divide your data sets into b blocks, and you can take b minus 1 block for the training and 1 block for the testing. So you can divide it basically 10 parts. So if you will take 10, so you can take 90-20 or 80-20, and you can do anyways. It is not necessary to follow some kind of rules. Okay. uh Fine. So now what we do is that we firstly, after finding the regression coefficient, we try to find the residual values. And after finding that residual values, we try to obtain the mean square error, obtain along with that residual. So the first thing we do after calculating all of this, we try to find this uh, yi minus y summation. Okay, this one is from j1 to k, this one is from i1 to n. So this is the residual sum of squares, and then we take the mean sum of squares. So this one will be 1 upon b, and that summation rss. Okay. Okay, now to implement that in R, so I have not, because the data set we have taken till now, this one is uh, just for three parameters. So I have taken uh, the data set which is already in R. So in the very starting, I have said that there are a lot of data sets in R already. So let me show you if this is needed. Okay. Okay, so this one is regarding this only. So basically, what you can do is that there are a lot of packages inside it, and In that packages there are a lot of data sets. So uh, there is a data set in R saved already, which is named at empty cars. So this data set, okay, let me do this. Okay, so this one will not come like this. Okay, so here as you can see that there are some data sets, uh, like studies on effect of elevated CO2 levels. Then there is biomass data set. So you can see that there is a package robust base, and if you library take that library, then you can make use of this data. So there are a lot of data sets which are already in the R, so that you can see. So currently I have taken this empty cars. So this have some parameters, and this have some uh, cars. So we what we are doing is that we are taking some y variable as this empty cars and then hp1, and the x I have taken as this mpg, this yt, DRAT, and QSEC. So these I have taken as the basically as the dependent independent variable, and this is I have taken as the dependent variable. So we have one independent variable and four dependent variable, and out of four we will see what is working. Okay, so firstly I will search for that. So okay. Okay. So now we will see firstly what is given here. Okay. So x is a matrix of explanatory variables. So we have given these four variables as explanatory variable. Y is the vector of objective variable. The family of regression is Gaussian. So family of regression basically that epsilon one. So we have that Gaussian errors. The next is implementation language of optimization. So the CPP is the default one. The R is the we can take the R also. Just a minute. Okay. The next thing is the ratio of maximum lambda and the minimum lambda. So if we want to give that the maximum lambda uh, and the minimum lambda needs to be in this ratio, then we can give it. Otherwise, we can just ignore it. The next is n lambda, so the number of lambda. uh, the next one is the sequence of it, and then this, and the values it gives us is it gives us the beta, the coefficients one. The beta is standard, which is a standardized coefficient. The a naught, which are the intercept. So basically in the regression fitting, what we have the regression coefficients, we have the intercept. So we will have the same values here. uh, okay, and the lambda, which are regularization, so basically which are regularization parameters, or which are the constraints we are giving to our model. The family is the regression family. So we have said, okay, so we have taken the x and we have taken the y, and I have written that lasso as x comma y. Family is the Gaussian, and whatever is written here. So I have just taken the same one. N lambda I have given as 5, and the lambda is equal to none. Okay. So now if I will run it, okay. So it does not have this. Okay. So now you can see we have got these values. We have got beta standard. We have got the lambda. We have got this alpha, delta. We have got the beta, the a naught, which are the intercept terms, the attributes, and the family is Gaussian because we have in the very starting we have given this family as the Gaussian. Okay. So now this beta is standard. So this one is, as you can see, uh, okay. Okay, so irrespective of this 1, 2, 3, 4, 5, we will have these values of a naught, which are 1, 2, 3, 4, 5. We will have these lambda value, and if you see the standardized, the this one is the beta standard. If you will see the beta values, then it has given also here. These are the above values are the lambda values. Okay, and these are the values of the beta coefficients. So this is 1, 2, 3, 4, and 5. Okay. So if I will say with, let's say, L1, and if I will try to find this L1 beta, then I can have all these values. Uh, Now, uh, after doing this, we need to do what we need to do is that we need to draw the calculate conclusions from it, and we need to decide from this outcome. So firstly, what we need to do is that we need to see what are the values which are close to zero, and variable corresponding to these values, we will just like if I have something beta, let's say beta 3 is 0, is near 0, then obviously the x3 will be removed from it, and the too small value of lambda, that can lead to the overfitting of the model, and that can create the noise in the data. On the contrary, the too large values, that can also create the problem for our data. Okay, so now the n lambda we had is 5. So you can see the nearby value is 4.44. This one is over this one, the too large value, this one is underfitting, and these small values are underfitting, right? So you can see that this one is underfitting, these yes, this and this, these three are overfitting our model, correct? uh, so Okay, so now related to that lambda, what we'll have? So below each one, so values under each of the lambda, these are the provided for the sixth regression coefficient. So if we try to observe, so for these values are given for the coefficient, this one and this one. So you can see that how it is underfitting. So basically, when it underfits, so it says that underfitting basically means that this one is also not important, this one is also not important. So it will try to fit in the minimum number of parameters. So you can see that it has given this also 0, it has given this also 0. So it is just saying that only two are important, and this also is very near to 0. So only one is important. So that means this is underfitting our model. Whereas if you will see these values, then these are overfitting our model. So you can see that it has increased. At when it is 0.044, it is 1.8. When it is 0.044, it is 4.5. And when it is 0.004, it is again increased. So it is also saying that it is overfitting, whereas in the 4.45 it is 0. So it is not important. Okay, so once we have seen these values, uh, at lambda is equal to, because our lambda was 5, so the near one it is 4.445. This one, these are the values which are underfitting, these are the values which are overfitting. So these are the coefficients which are fitting our data. So from here, what you can conclude is that MPG, WT, and QSEC, these are affecting our model, and the DRAT one is not affecting our model. So this one will be removed from the model. Is it clear? Everything? Okay. And the so our final model will be, so you can see that this one is our the lambda where it is satisfying. So these are basically minus 3x1 plus 19x2 minus 18x4, x3 is removed, and the intercept term is given by the a naught. So for that a naught, it this one will come as the, because according to the lambda, so lambda is for the second value. So this one will be 47, 476.9099. So our model from that can be written as 476.9099 plus, uh, or just write minus 3.109897 x1 plus 19.041698 x2 minus 18.432915 x4. So this one is our final model. This one is our final lasso selection model. Based on that lasso, what we have concluded is that first, second, and fourth parameter is important for our model. The third parameter is not important for our model. Okay, so if there is any confusion, anything, any problem, then you can ask right now. Okay, and if there is no problem, what I will suggest is that try to find more of the data sets in the basically our library itself have a lot of data sets. So you can try fitting that, and you can try to do the conclusion based on this. What else you can do is that let us just do one more thing, which is, let us just do one more by taking different value of lambda. And now, seeing this. So here what I have done is that I have taken a different value of beta. Now you need to select from here. Uh, like this 15 point this uh, uh, will overfit the 5 sorry underfit the 5.71 is underfitting, but you can see that the almost results are uh, this one is changing, but for these are almost same. So you need to find something in between which will be good for your model. So that means this one is completely not gonna take, for this value is not gonna take, and after this these are not gonna come, but between 15 and 5, because we have given as 10, so between 15 and 5 you need to see that which one works better for your model. So basically, thing is that the dread is still not contributing, but in between all these three, how much one is contributing. So that are some questions you can ask from yourself, and you can try to solve that. Okay. So these are the work we have till for today's class. Now tomorrow is the extra class or the revision class. For the revisions, I have taken almost all the points from the starting, so that you can we just go through all of it. Uh, and if there will be any questions, then you can ask in the last class, which is tomorrow, and if not, then it's okay.
Do we have tomorrow extra class?
Y- yeah, you should have got the mail. I have got the mail let me show
Okay.
you. uh
Actually, I am facing difficulty. I have downloaded the Lasso, but
huh.
still it is not getting that installed.
Yeah, so that is why I
The
asked now
same issue continues.
to share your screen, then let me see that what is the problem. Okay, so I'm just
Okay,
removing my
this
screen.
says the library when I'm error in library Lasso. There's no package called Lasso. So
So that is why you can just present your screen. I'm stopping my screen. Okay, I'm stopping presenting that. Okay, ignore.
I have downloaded it. This is the link which you forwarded.
Yeah, I have got it. So you just do it here, and then we will see what is the problem so that you can install it.
Shall I share the screen?
Yeah, yeah, you can share the screen. I have stopped presenting already.
Okay.
Here I have got this mail. Uh, it is loading still. Okay. I cannot see your screen in case you're presenting, so I don't know.
Okay. Let me. I need to. I need to. Let me. Do I have any share?
Yeah, in that share, just do the
Okay.
entire screen, and click on that entire screen again.
Okay. That print I have done it. I have
Hmm.
to add it now. I have to send it. So share. Okay.
In the present now, click on here in my
Yes. Yes.
in the present now.
Yeah, yeah, yeah.
You
I'm
go
just
to the entire screen, last one, and again click on the entire
yeah.
screen. Okay.
Just I've shared it.
Yeah. Okay. Yeah. So, uh, okay. So you what you need to do is that write it like this: install those packages, and you just write this command. Okay, and then tell me if there is an issue. I,
Okay.
I am writing in the chat one. Okay. So from
Install
my chat,
package.
just copy everything and then write it here.
Okay. Okay.
हाँ पगल है ये तीन दिन बैठल नहीं है ये दिन बैठल नहीं है
We have to. We have to
ना गइल नहीं आई का डॉलर
type
बना दी
it.
नहीं
No, in my go to my chat. Go to my chat. The Google Meet chat. Go to there, and in that chat, I have written install dot packages, and in between that, I have written this.
I hope now it is installing. Just I was just mistaking somewhere.
No, it
That
is still
thing
not
gives.
installing. What it is showing that uh, that dependency, these are not available. Okay, so you also have this problem of this dependency. Okay, so because I had the same problem, what you need to do is that just copy this in your R studio, that the untitled one, na? Just copy it there, whatever I have written. Let me just show.
Okay, okay, ma'am. I have copied it now.
Okay, so okay, so
Yes, ma'am.
here I have written like here. Okay, so what you need to do is that firstly, do the R tools. You need to install the R tools. R tools.
R tools I have downloaded, ma'am. R tool 44 I have downloaded,
Is
and I
it?
have installed also.
I have downloaded R tools 42. So is it like matching to your work? Like if it is, this one is 4.2. Mine one
I
is.
have installed R44. Let me say that one, ma'am. Uh, I had downloaded R tools 44. Let me say that also.
Okay. Firstly, okay, I do not know all of it, but uh okay, just stop presenting. What you need to do is that install that R tools which are related to your R studio. Okay.
Okay, right, ma'am. So that is 42, I think.
Okay, for me it was 42. So you need to check it from your side. So you need to just Google that what is your R package one, and then according to that install that R tools. And then like I have asked the chat GPT just for that why it is happening. So it has says for me it was the make function was not there. So I have just checked that whether in my system the
Okay,
make one is here or not. So once it was here, it has installed that R package, this ilaso package. So if it will not install even
okay,
tomorrow, then you can ask. So firstly, just see that what is your R package, download the R tools for that.
My R package is 4.5.0.
Okay, so that you need to install the R tools according to that, I think. R
Okay. So, what is your package, ma'am? वैसे
which package you are running with?
Uh, yeah, there is like R tools.
4.4.3 or 4.
For me, it was 4.2. Now, if I can see that there are R tools for 4.5 also. So if you have downloaded for 4.4, it will not work.
Okay,
So download for R tools 4.5 version. Okay.
4.5 version. Okay, if it is R 4.5, then right, ma'am, we'll do it.
Yeah, here. So if you can see, there is R2's 4.5. So do it for R2's 4.5 and then check in your system whether the problem it was creating, like if when you are doing that install dot packages and whatever the problem it was creating, that RH and BP something was not there, whether it is there in your system or not. So after that you can just see whether it is
Okay,
working or not. Okay.
okay, ma'am. So tomorrow there will be class.
Yeah, I mean, I have got the mail already that in, like, let me check. Uh, I have got the
Because since
mail
I was
at,
unable to install this LSO, so I could not practice some of the questions and also the assignment which was given.
yeah,
Though the first five, six, seven questions I have already completed, first seven,
huh.
but those three questions based on the lasso I could not practice on the R software.
Yeah, that is why I said, na, you can just check from there, or otherwise, if it will be problematic, then we can check tomorrow. And
That I will download now. Now I will try to install 4.5
yeah,
R
and
tools and
and
then we can
then
proceed.
just check on the chat GPT, like what is the problem happening even after installing. It
Yes,
will
yes, ma'am.
give
I
something.
just try to resolve from the chat GPT.
Yeah.
Uh, they also suggested some other sources that to download from there. I tried it, but could not succeed.
Yeah, they have also uploaded in this, like updated in the site that there is a class tomorrow, April 16. So I will take.
Okay, right now. I will try, and then if I am unable to, then we'll speak.
Yeah, sure. Okay, then thank you for joining, and I'm ending the class.
Thank you.